Hello everyone, Aaron here, and welcome back to Leetcode. Today we are solving the path with minimum effort problem. The context today is that we are a hiker, and we are trying to get from the top left to the bottom right of this height map. So here, for example, we're at height 1, this would be height 8, and this would be height 5. We're a bit of a lazy hiker, and we want to do this with the minimum effort, and the effort is the absolute maximum difference. So on this path, the highest point is 5, and the lowest point is 1. No, it's a consecutive distance, sorry. The 1 to 3 is 2, 3 to 5 is 2, 5 to 3 is 2, 3 to 5 is 2. So here we have an absolute maximum difference of 2. If we were to do this one here, 1 to 2, 2 to 3, 3 to 4, 4 to 5, all of these have a difference of 1. And this one here, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. There's 0. There's no difference at any point. So, I'll admit when I first saw this one, I was expecting it to be a graph search problem. I think it is still a graph search problem, but it is a bit of a strange one. So, let's set up a graph search. And I think we're going to do something vaguely in the style of Dijkstra's algorithm. So the way Dijkstra's algorithm works is you start at the start place and you basically start sending out feelers in all directions, always picking the least cost step forward. The trick is here that the cost is going to be a bit funky. So for here, 1 to 3, we would say the cost is going to become 2, but to go from 3 to 5, we could probably argue that the cost is 0, because it doesn't actually increase the overall path effort. Anyway, let's code up Dijkstra's algorithm. Now, I haven't been having a lot of success in TypeScript for the last couple of graph search problems, so I'm going to go into Python, just because I know it a little better. Because we're going to do Dijkstra's, I'm going to import the heapq library because it gives me heaps. And Dijkstra's is all about taking the next lowest cost thing, which is sort of a minimum priority heap kind of problem. So, the minimum effort path, let's go self.height, something like that, just to kick us off. Now the way Dijkstra's work is we need to keep track of everything we've seen, which can be a set. And self.best so far for each coordinate is going to be a dictionary. And then what we want to do is self.edges. This is going to be our heap. It'll start empty, and we're going to add to it as we go. Start can be 0, 0. End is going to be len self.heights len self.heights -1, or 0 would also work fine, I guess. So while end not in scene, the way Dijkstra's algorithm works is we want to go heapq.heap pop self.edges, and what we're going to get from that is it's going to be the cost And let's do source target. I haven't decided what we're exactly going to put in this heap yet, but I think it's going to be basically the cost. If we were to go this way here, for example, it would be 2, and here it would be 1. But if we're already here, the cost would be 0 because it wouldn't increase the path cost any more. And source and target is, of course, just the coordinate system 0, 0, 2, 2, so on and so forth. When we take something off the queue, by the very nature of Dijkstra's algorithm, source will have already been seen, but target will not have been. So we're going to lock that in. Self.best so far. For the target, we're going to make that equal to the cost. Actually, how do I want to do this? No, I think I want to do this slightly differently. I think I want to turn this into a target path pair. Self.cost of the path. So we're actually just fully doing it. And then what we want to do is force neighbor in self.neighbors path actually no, hang on. How do I want to do this? I think what I want to do is I want to have just a path here, and target is path -1. So the very last thing on the path is the target that we got to. So for example, 0, 0. So a path might look like, for example, 0, 0, 0, 1, 0, 2, 1, 2, 2, 2. That would be a path. So the target would be this last thing, for example. For neighbor in self.neighbors path, heap queue.heap push self.cost neighbor. Oh, hang on. Yeah, that's fine. Let's call it path 2, just because it's an extension of path. And it's going to be self.extend path. So we add them all to the heap. Now we need to check for the end when it's in scene. After this, just because if we were to see it here, that doesn't mean it's the best way to get to it. It just means it's the first way we've found to get to it. So we need to wait till it's come out. So then what we want to do is return self.best so far of the end. Now, this is quite good, but we do need to fill in a couple of gaps. So let's do, what are we missing? We need cost. And we need extend path. Well, let's do the cost first. So what we want to do is, well, let's set up the diffs. For I, j in zip path until just before the end, path just until there. So this, if you've not seen it before, is a fairly common Python idiom. The idea is that we're going to lock the thing off the end and we're going to lock the thing off the front and two separate instances of it. And so then what that's going to do is it's going to give us these two, these two, these two, these two as pairs ij. So it's going to be self.heights I0 I1 H2 is going to be self.heights J0 J1 diff is abs h1 minus h2. I could do this all in one line, but I'm not going to. Let's do min cost is equal to infinity if diff is less than min cost is diff. So here we're looking at 1 and 3. That's a difference of 2. 2 is less than, no, hang on. We want negative infinity and we want to do max because it's a max cost. In fact, no, let's make it 0. Let's start at 0. So if the path is just 1 by itself, 0, 0 by itself, then we're not going to actually do anything and the cost is 0 so far. Then we go to 1 to 3. So we're looking at the 1, 3. 3 minus 1 is 2. 2 is greater than 0. 5 minus 3. Okay, that's fine. Now, the trick is, have I set this up correctly? I think I have. Anyway, so this will carry along and it would constantly say that the max cost is 2. Extend path now. So what I want to do is I want to go target is path -1. And then what I want to do is I basically want to do up, down, left, and right, as long as they are both on the board and not in the path we've already taken. So the next steps here can be target 0 minus 1, target 1 minus 1. In fact, no, it can't be that at all, but hang on. There's 4 options. -1, do nothing minus 1. +1, do nothing plus 1. So what we want to do is we want to return n in next steps. IJ for IJ in next steps if I is greater than 0 and j is greater than 0, and actually let's do self.width is len self heights 0, self.height is len self.heights. So the end here is at height width at -1 on each of those. And I is less than self. Need selfs in front of them. Self dot height and j is less than self dot width. These should be greater than or equal to 0, not greater than strictly. And ij not in path. And I want to make sure these are full paths, so I'm going to splat them together. Now this thing is a little bit of a monstrosity, but we can break it down. So for everything in the next steps I talked about, I want to basically glue it onto the end of the path I'm extending. But I only want to do that if it's going to be in the board and I haven't already been there. There's no point walking back to somewhere I've already been. We've just done a little loop that we could have cut out completely. In fact, this would be even faster if we did not in self. No, not in path. No, that's fine. Heights. Got a width and a height. We've got a scene, which is an empty set. So to kick it off, we actually need to do self.scene is equal to the path containing the start only. No, self.scene. No, self. Hang on. Heap queue.heap push 0 and the path containing just the start. So what this will do is it's going to push a path that's of 0 cost that is just the start onto the beginning. And in fact, I don't need to run self.cost for that. I can just run cost. I can just put cost in there, can't I? Because now, oh, hang on, let's do a complete run through, shall we? Height, so this is heights. We know it's width and height. We haven't seen anything. We don't know the best so far. Start is 0, 0, end is here. We're going to push the start with a cost of 0 into the edges. So hang on, let's maintain a little edges here, which is initially going to be 0, 0, 0. And then what's going to happen in here is we're going to pop that off. So cost is going to be 0 and the path is going to be, so that's going to be our cost and that's going to be our path. Hang on, let me So that's our cost and path now. And then we're going to have best so far. Hang on. Target. When we make target, that's going to be the 0, 0. Self.scene. Okay, hang on. Let me just put these back in here for a moment. I think this is all the information. So when we kick it off, we're in this particular state. So we take this off. And then the target is the 0, 0. So the best so far for 0, 0, we say is 0. And then we want to extend the path. So to extend the path, we're going to do a version, well, we're going to end up with some cost for 0, 0, some extension on it. And we're going to end up with, well, we should end up with 4, but we're only going to end up with 2 of them. One of them is going to be at 1, 0. And the other one is going to be at 0, 1. And the cost for this one is going to be 2. And the cost for this one is going to be 1. So this all gets cleared. We take the best thing off, and that's actually this one over here. So that gets put there. The target is 0, 1. So the best so far for 0, 1 is 1. Then we want to extend it. We're not going to extend back this way, but we are going to extend down and across. So we're going to push on now some new information on, hang on, it's going to be that, it's not going to have those. It's going to then go to either 0, 2, or it's going to go to 1, 1. Gonna have to move that across a wee bit. The cost for this 0, 2, 1 is the cost of the whole path, so that's still just a 1. And the cost for this one here, well, that's a 1, but that jump is a 6. So the cost for the whole path is a 6. This trace is going to take forever. Then the next best one is going to be this guy. In fact, I want to cut it out completely. So the target is going to be 0, 2. The problem is we're going to walk a long way this way before we realize that's really expensive. But that's the way it is. So the best so far for 0, 2 is 1. And that makes sense. That would be the best way to get there. Right, how do we extend it? Oh, it's gonna, okay. Hopefully this trace is kind of getting the point across, because right now this is going to take 1,000 years to do by hand. So what I want to do, I think, is run it and just see if we're passing the test cases. We're not. Heap push expected 2 arguments, got 1. Oh. I have to tell it which heap I'm pushing onto. That's a silly mistake. Wrong answer. Oh no. Output 0. I wasn't consistent in my rename. Silly mistake. Right, that looks better. Let's use all of the test cases. And we pass all of them. Excellent. Fingers crossed. Let's see how this goes. Looking slow. Time limit exceeded.
5 minutes later.
No.
2 hours later.
No. We're exceeding the time limit.
1 eternity later.
Hi guys, Aaron again. I was just faffing around with this path with minimum effort problem again, and I realized I hadn't added in this. If I try to explore somewhere I've already seen, don't bother exploring it again. Now, that's because there's two places where I should check this condition. One is when I'm extending the path, so I should make sure I'm not trying to extend it into somewhere I've already seen. But also, if for some reason I come back around to trying to, if I find another way to get somewhere and it's not the best I've seen, don't bother. So I should have done this check. Now, it didn't end up being a problem, but it did end up saving us quite a bit of time, I think, because I've been running that massive test case and it's actually started passing. So let's click submit and see what happens. Oh, thank God. Holy crap. All right, that one was ridiculous. I'm annoyed I forgot these 2 lines. So I'd hate to think how much we can simplify this, actually. Yeah, Jesus, this would probably be able to be massively simplified now. But I'm not going to touch it anymore. So, with a slightly happier ending, we've finished the problem. Somehow. Again, thank you very much for watching. You're going to get 2 problems today. So yeah, thank you very much for watching, and I will see you tomorrow. Bye. Holy crap.